Hello, welcome to this presentation. My name is Tianyu from the Hong Kong Polytechnic University. I'm glad to be here to present our recent work, which is a system work, and we study wireless network scheduling problem. This paper is entitled APaS, an adaptive partition-based scheduling framework for 6TiSCH networks. And this is a joint work from UConn, Polyo, and Notre. Okay, nowadays cyber physical systems are everywhere, from small buildings to medical devices to automation. And as a critical role, real-time wireless networks are fundamental to many CPS applications in a broad range of fields where real-time guarantees are really critical. And among these many emerging real-time wireless network technologies, 6TiSCH has been receiving increasing attention in recent years. It is developed by IETF and has a nice feature of going real-time link layer standard together with an IP-enabled upper layer stack. We created a 122-node 6TiSCH network testbed and have presented a demo to demonstrate the functionality of the APaS framework we propose in this work for 6TiSCH networks in the first conference day. And these are all 6TiSCH devices in our testbed, and these nodes are spatially distributed in the computer science department building at UConn. Benefiting from our testbed, we observed that the current network management in 6TiSCH is still under development, mainly due to its built-in random-sized packet scheduler at the data link layer, and it can cause relatively high transmission latency. For example, this figure shows the topology of a 5-hop 1-node 6TiSCH network in our testbed, and we measure the uplink latency experienced by each node. The framework length is set to be 1.27 seconds, and from the result, we can see that many nodes experience end-to-end latency larger than the slot frame length, and the latency increases with the hop count. The average uplink latency of the 5-hop flows can reach 3.38 seconds, which is almost 3 times larger than the slot frame length. And considering those harsh industry environments which may cause nodes to frequently change their parents to seek for better communication links, this case can be even worse in such dynamic network topology scenarios. So to address these problems at data link layer for 6TiSCH networks, we aim to design an adaptive link layer scheduling framework. This framework should be able to provide guaranteed E2E latency, particularly within 1 slot frame length. And given the large-scale deployment requirements of 6TiSCH networks in industry applications, this framework should support high network scalability, that is, to enable more devices running the network. Also, this framework must be adapted to network topology changes. We realize these functionalities by proposing APaS framework, which consists of a baseline partition-based scheduler and an improved 2-dimensional version, and also a dynamic partition adjustment method. Below, I will first describe the system model studied in this work. We adopt a typical real-time wireless network model in which sensors and actuators are wirelessly connected to a controller node, which is also called gateway, either directly or through one or multiple relay nodes. The network topology is modeled as a tree, and the root node represents the controller. Each link is associated with 2 attributes, type and layer. By type, we mean uplink or downlink, and the layer of a link is the child node's hop count to the gateway. The task set running in the network consists of a set of periodic multi-hop unicast tasks and a broadcast task. Each unicast task is sent out from a sensor node, passes through the gateway, and arrives at an actuator node. A broadcast task is generated from the gateway and is responsible for broadcasting a network-wide configuration information to all the nodes in the network. The 6TiSCH network deploys a TDMA-based data link layer and adopts a centralized link-based scheduler to allocate network resource for individual links. The basic resource unit that can be allocated to individual links is called as a cell, identified by a time slot offset and a channel offset. Based on this system model, we further make 2 assumptions in this paper to clarify the focus of this research. The first one is the end-to-end latency assumption, where we only consider the end-to-end MAC layer latency and ignore the latency introduced between the application layer and the MAC layer. We make this assumption because the data link layer scheduler is not aware of the generation time of the packet at the application layer, which can be arbitrary. And the second assumption we made is that we assume for each task, the number of cells required by each link along its routing path has been determined, and each task is assigned with sufficient number of cells to transmit. That is, we do not consider the cell number determination, which has been already started quite a lot in the community, and only focus on the cell allocation and adjustment problems. So we need to answer the question that how to allocate and adjust cells in the slot frame to achieve guaranteed end-to-end latency, high network scalability, and also be adaptive to topology changes. Next, we describe our adaptive partition-based scaling framework, APaS, in detail. We first use a motivating example to demonstrate that different cell allocation strategies can significantly impact the end-to-end latency, and two observations we got from the motivating example to help us design the APaS framework. So let's consider a line topology, and the task is generated at node A and sent to the destination node R. So suppose we have a link-based schedule following the inverted order of the routing path of this task like this. We can say that after each transmission of a single hop, the task has to wait for the assigned cell to transmit its next hop in the next slot frame, and totally it needs 4 slot frames to complete the transmission. On the other hand, if the schedule follows the right order of tasks routing path, the transmissions of all its hops can be done within 1 slot frame. So this comes to the first observation that the cell allocation following the task routing path sequence can lead to a shorter end-to-end transmission latency. Now suppose a new node E joins the network and a new periodic task from E to R is generated. Now we need to allocate an idle cell in the schedule to the new link E to C. Then even using the schedule combined with the task routing path, we still need another slot frame to transmit this task. The root cause here is that we cannot satisfy the good property in the previous observation for the newly added task that the cell allocation is compliant with the task routing path sequence. Well, if we reserve an idle cell here before the new link being added, then we can still only use 1 slot frame to transmit this new task. This example indicates the second observation that we should reserve some idle slots to help satisfy observation 1 when topology changes occur. Then we need to determine how to satisfy these 2 requirements simultaneously, especially where to reserve those idle slots in the slot frame. So our solution is to use slot frame partition. Specifically, we found that the routing path of task is highly related with the link's layer attributes. So we divide the slot frame into partitions according to the layer and type of links. Each partition is dedicated for a certain type and layer. For example, here, U3 partition can only schedule uplinks in layer 3, and all the partitions must be compliant with the routing path. With such partition-based scheduling framework, we prove that the end-to-end latency of each task can be bounded by 1 slot frame length. But only with this partition-based design is not enough. We need to determine how to assign links into each corresponding partition that is performing the cell allocation. Here, the cell allocation suffers from a constraint that cells with the same slot offset cannot be allocated to links with the same sender or receiver. For example, A to R and D to R cannot be allocated into cells in the same time slot. This is because they share a same receiver node R, which cannot receive signals from multiple senders simultaneously. So with this constraint, we design an optimal cell allocation policy which can use a minimum number of needed slots within each partition to accommodate all the given links. In this case, we can have more idle slots reserved for future dynamic topology changes. Well, while speaking to topology changes, if a new link In layer 1 as into the network, we found we cannot assign it in the schedule because all the links in layer 1 share the same receiver, and there are no more idle slots available in partition U1. Even we observe that there exist idle slots in other partitions, we cannot use them since the baseline partition framework requires that one partition is dedicated for a certain type and link. However, this requirement introduces an unnecessarily strict time order dependency. For example, transmission E to A does not need to happen earlier than C to R, since these two links can never be on the routing path of a same task, so they do not necessarily have any precedence relationship in the slot frame. This insight motivates us to perform partitioning not only in the slot frame dimension, but also in the channel dimension. The key idea here is to relax the order constraints of links in the time dimension. At the highest level, we first divide the slot frame into multiple rows, each of which consists of a set of channels and perform the baseline partition method for each row. Then we have a new slot frame layer like this. Next, we need to assign links into the partitions in each row, and this is done by letting all links belonging to a same branch into partitions in a same row, such that their routing sequence can still be guaranteed. While links belonging to other branches which have no sequence constraints can be assigned to partitions in other rows. So essentially, two-dimensional partitioning lets links in higher layers to borrow cells from lower layers into partition and enable partition overlap to improve the cell utilization in the network. And we can see here this partition overlaps in the channel dimension help condensing the total length of time slots needed. While although the two-dimensional method improves the network scalability, when the network size grows with new node adding in, it is still possible that some new links cannot be accommodated in the corresponding partition. In this case, cell allocation requests may not be fulfilled if topology changes and dynamic partition adjustment is desired. A dynamic topology change can be classified into different cases. First, the cell allocation request decreases. This happens when some existing node leaves the network. In this case, we just simply release the unused cells in the schedule. The more complicated case is that the cell demand increases when some new node joins the network, and at the same time, there's no idle cell in the corresponding partition. In this situation, we need to adjust the partition boundary or shift all the cells into partition to generate some idle slots. To keep the runtime overhead under control, we do not perform such adjustment immediately, but either periodically or based on certain loading condition. Before the adjustment, we allocate the new links into some areas where these cells cannot be used due to the cell allocation constraints, and we call it temporary area. Using these temporary area cells, instead of randomly selecting idle cells in the partitions, the benefits is that it will not hurt the routing path property of other packets and their end-to-end latency. For the details of this dynamic adjustment method, readers can refer to our paper. Okay, next I will show some of our evaluation results from both simulation and testbed. In the simulation started, we compare APaS with the baseline randomized scheduler RTAS and two state-of-the-art low latency scheduling functions designed for 6TiSCH networks in the literature, LSS, F, and LDSF. The metrics we use to make the comparison are end-to-end latency, EL, and the success ratio SR defined as the percentage of packets satisfying the bounded one slot frame length latency. Here is a snapshot of our simulation. This is a 100-node network topology and the schedules generated by our APaS, the RS scheduler, and the LSF and LDSF. For static networks, here the dashed line represents the length of one slot frame, and we can see that RS demonstrates the highest end-to-end latency and lowest success ratio. For the rest three methods, although all of their average end-to-end latency are within 1 slot frame length, the success ratio of LRSF and LDSF drop to 80% when the network size increases to 160, while APaS always achieve 100% success ratio. And in the dynamic scenario, we generate 50 continuous interference events on a 100-node topology, and the interfered nodes will disconnect with their parents and associate with new parents. It can be observed that the end-to-end latency and the success ratio of both LRSF and LDSF are significantly affected by each dynamic topology change event, while the performance of APaS is relatively stable and guarantee a 100% success ratio. Now let's move to our testbed evaluations. Since many detailed results have been shown in our demos, so here we only give a sketch. In both static and dynamic scenarios, APaS maintains stable end-to-end latency and success ratio values, while the SSRs of LSF and RS decrease a lot. The testbed results are consistent with that of our simulation. Only difference appears in the performance degradation for all the methods in the testbed experiments because of link failure and queuing delay in real world. Okay, here comes to a short conclusion. In this paper, we proposed the APaS framework for 6TiSCH networks by applying the concept of resource partitioning. APaS can guarantee an end-to-end latency of any flow within 1 slot frame length and adapt to dynamic topology changes. As future work, we will extend APaS to distributed setting and explore effective machine learning methods to better handle network dynamics.